Alrighty, good morning everybody. Welcome back to Math 105. Plan for today is we are going to continue our discussion of Standard 9, which we started last Friday. And continue talking about some techniques that we can use to read and write mathematical proofs. I've got my usual office hours today at 10 o'clock and from 2 to 3, and my usual hours tomorrow from 10 to 11:30 and 1:30 to 2:30. And no homework for today. How about that? Standard 8 quiz has already been due. The Standard 9 quiz, just so you know, we're not going to finish Standard 9 until Wednesday's class. And I plan on making the Standard 9 quiz due maybe like Monday or Tuesday after fall break. So for now, there's no homework assignments for you today or anything. Any questions or comments before we get started today? Okay, so an engineer, a physicist, and a mathematician are subjects in a psychology experiment. This one's a long one. This is I need to bring the book. After not eating for 24 hours, each of them is locked in a room with a can of food, but with no can opener. But they are given some paper and pencil. So at the end of the experiment, the psychologists go to visit all their rooms, the engineer, and physicist, and the mathematician. So they go into the engineer's room, and it turns out that the paper and pencil were unused, but there are dents all over the wall. Engineer threw the can against the walls until it split open, and is eating a nice, meal of beans. They go into the physicist's room next. The paper is covered with formulas, and there's only a single dent in the wall. Physicist is also eating a can of beans after she calculated how to best throw the can against the wall and was able to do it in a single throw. Finally, they go into the mathematician's room. The mathematician's paper is full of formulas. The can of beans is still closed. The mathematician is nowhere to be found. There are strange noises, however, coming from inside the can. So psychologists quickly use an opener to open the can, and the mathematician jumps out of the can saying, "Darn it, I got a minus sign wrong." Kooky mathematicians. Okay, so you may remember from class last Friday, we actually proved 3 different mathematical statements by showing that where all of these were implications, and we proved each of these by showing that under the assumption that the if part of the statement is true. If the hypothesis is true, we showed the conclusion had to also be true. And in doing so, we proved that if A and B are both even, then A plus B has to be even. If A is even and B is odd, then A plus B is odd. And finally, we showed that if A is an even number, then A squared has to be even. And for all of these were all implications. We only needed to prove stuff in the case where the hypothesis is true. So for the first one, we got to assume that A and B were even, and then just logic out that A plus B had to be even as well. If either A or B was not even, then A plus B did not have to be even, and we didn't have to show anything for all of these. And so that's where we left off on Friday's class, is looking at these 3 statements. Today I want to talk about a couple other proof techniques that we can use beyond just assume that the hypothesis is true and show that the conclusion is also true. So I'm going to be on the, 3rd page of the packet. And the claim I'd like to prove today is that if A squared is odd, then A is odd. And as a quick reminder, we said that A is even. This is the definition. If A is equal to 2n for some natural number n. And A is odd if A is equal to 2n plus 1 for some natural number n. And so now, what I would like to do is to show that if A squared is odd, then A has to be odd. I claim we've already proven this, and there's nothing more we need to prove. So this claim is actually a little bit sneaky in that it may not look like something we've already proven. If a squared is odd, then a is odd. But I claim this is logically equivalent to something we've already proven. So what do you all think? I claim this statement, if a squared is odd, then a is odd, is logically equivalent to one of the three statements we proved on Friday's class. Which one of those three statements do you think is logically equivalent to saying if a squared is odd, then a is odd? Yeah, Blake?
If a is even, then a squared is even.
So why do you think those two are logically equivalent?
It seems like the contrapositive, kind of.
It's not just kind of, it is the contrapositive. Yeah, that's exactly right. Turns out, this claim is just the contrapositive of this third claim from Friday. And as we've seen from several previous standards, any mathematical implication is always going to be logically equivalent to its contrapositive. Meaning if this is our statement P here, a squared is odd, and if this is our statement Q, that a is odd, remember that the implication P implies Q is logically equivalent to not Q implies not P. So P implies Q is logically equivalent to its contrapositive not Q implies not P. I.e., in this case, not Q implies not P would be saying if A is not odd, then A squared is not odd. These are logically equivalent. What we say in the claim, if A squared is odd, then A is odd. And if A is not odd, then A squared is not odd. But since all numbers that are not odd have to be even, we didn't prove that, but we're just going to assume that for now. We'll actually prove that later in the packet. If A is not odd, then A squared is not even. That's just the same as saying if A is even, then A squared has to be even. So this says the same thing as if A is even, then A squared must also be even. And since we've already proven this statement, we don't have to prove it again. We could just say, oh, this is something we've already proven, and therefore, since we proved that this implication is a tautology, that it's always true, that's then going to tell us our original claim must also be a tautology. Since this has been proven to be a tautology, our original claim must also be a tautology. Any questions or comments? So that's one kind of cool thing I think about being able to prove these mathematical statements, is that when you have a claim like this, if A squared is odd, then A is odd. If A is even, then A squared is even. Once we prove a statement like this, that then tells us automatically not only must this statement always be true, but any statement that's logically equivalent to this implication must also be true. So if this is true, then its contrapositive also has to be true, and the same for the other two implications we've proven so far. We could also say if A plus B is odd, then then A and B can't both be even. Or if A plus B is even, then we can't have it so that A is even and B is odd. Once you prove a mathematical statement, you've also proven its contrapositive at the same time. Or once you prove an implication, I should say, is true. So let's look at another example where this technique of looking at the contrapositive might be a helpful one for us. So if we look at the second claim on the page, our second claim says that if A times B is odd, then A is odd or B is odd. So here, I'm going to break this up into three base statements. This will be our P, that AB is odd. This will be our Q, that A is odd. And this can be our statement R, that B is odd. Let's see what would happen if we tried to prove this directly. Meaning, if we started with our assumption, assuming that P is true, and trying to show that Q or R has to be true. Well, if we assume that AB is odd, if we assume statement B is true, which is kind of our usual thing we do when we're trying to start writing a proof for something like one of these three things. If we're assuming that AB is odd, what does that tell us about AB? How can we write that in a useful way using our definition of odd numbers?
That it is equal to 2n for some natural number. Or sorry, odd, 2n plus 1 for some natural other n.
I was going to say, yeah,
I
just
thought
do it,
it
no,
would
make it even. Then AB equals 2n plus 1 for some natural number n. And if AB is equal to 2n plus 1, how can we make that a statement about A or B individually? Lots of blank stares, and I agree. I don't know where to go from here. In our kind of examples last time, when A is even, when like A and B are both even, we were able to do something like, oh, A is equal to 2n, B is equal to 2x, therefore A plus B has to be 2n plus 2x. We could just combine two things we already had. But the problem here is knowing what A times B is equal to, we can't say anything about A or B individually. Because given stuff about A and B, it's easy to combine them together to make a statement about A plus B or A times B. But given a statement about A times B, it's hard to split that back up into a statement about just individual A or individual B. So it turns out if we try and do the direct approach where we just assume statement P is true, we get stuck very quickly. We end up with AB is equal to 2n plus 1, and we can't do anything with that. And so life is sad. So instead, we can't try and prove this statement directly. Meaning we can't just start by assuming statement P is true and try and show statement Q or R has to be true. Statement Q or R will have to be true. A will have to be odd or B will have to be odd. In fact, they'll both have to be odd, but that's another story. But we can't quite get there with what we have. So instead, we have to think about what could we do a little bit differently that would allow us to still go ahead and actually prove this implication. So in other words, what would be a logically equivalent statement to P implies Q or R that we could try and prove instead of proving just P implies Q or R?
Could we break it into two implications? P implies Q or Q implies R?
Technically, that's not logically equivalent to P implies Q or R. It's very close, but it's not quite the same statement. So that's a good idea, but I don't think it would quite work. That would give us, that would end up proving a slightly different implication. Plus, I think if we did it that way, we'd end up stuck in the same way. We'd be, okay, if P implies Q, assume AB is odd, then AB is 2n plus 1, and we wouldn't be able to go anywhere from that. Good idea, though. What else could we try? Okay, so in other words, you propose we take the contrapositive of this statement and try proving that instead? Okay, let's see. So that's certainly true. The negation of P implies Q or R is logically equivalent to its contrapositive. Negation of Q or R implies negation of P. What would the negation of Q or R look like? How could we rewrite that as without having negation of a compound statement?
Not Q and not R.
Not Q and not R. So instead of proving P implies Q or R, what we can do instead is we can try and show that not Q and not R has to imply not P. And what I think is going to happen is that proving this way will be a lot easier than trying to prove it using the original approach. So let's see what happens. So our goal is going to be to prove the contrapositive of our claim. And if we know that the contrapositive is always true, then from what we've seen in previous standards, that will tell us our original claim also has to be true, since it's a logically equivalent statement. Meaning it's true anytime it's contrapositive, it's true. So if the contrapositive is always true, then the original statement would have to always be true as well. So now, instead of assuming statement P is true, we want to assume statement not Q and not R is true. So what would that look like? How could we write out not Q and not R here? Yes.
If A is not odd and B is not odd.
So we could assume A is not odd and B is not odd. Which is the same as making an assumption that A is even and B is even, I think. So here, this would be our negation of Q, and this would be our negation of R. So if we're assuming not Q and not R, that's just making an assumption that A and B are both even numbers. Awesome possum. So if A is even and B is even, how can we translate that into useful information about A and B using our definitions?
A equals 2n and for some natural number n, and then B equals 2x for some natural number n.
Yeah. Then A has to be 2 times some natural number, call it n, and B has to be 2 times some natural number, which you said x, right? Doesn't matter what we call them as long as we're not reusing any variables. Then A is equal to 2n for some natural number n, and B is equal to 2x for some natural number x. I like it. So here, we're just used our definitions of what does it mean for A to be even and what does it mean for B to be even. Okay? Now we know we have a way of writing out both A and B individually. So what can we do with that information? We'd like to be able to ultimately prove negation of P, show that AB is not odd. So what could we do next?
Did you say that AB is equal to 2 and x? Same with if you be equal to 2n times 2x, but you still multiple 2.
Yeah, you could just write out A times B using that A is 2n and B is 2x. So then A times B is going to be equal to 2n times 2x. And what does 2n times 2x come out to? 2nx? Careful. I think we have two different factors of 2 that show up.
4 and x. Hold on, I'm doubting myself now.
You're right.
I was gonna say 4 and x.
I think you're right. Because we have two different factors of 2. So these will combine to give us a factor of 4. And then we'll still have the n and the x out there.
Why is it 4? We're just trying to prove that it's an even number. It's still being a number.
Because 2 times 2 is 4.
Yeah, I get that, but we're not trying to prove what the actual AB is. We're just trying to prove that it's even.
Still a multiple of 2.
It's because either way, we're going to get a multiple of 4 by definition. We don't need that this thing is a multiple of 4. That's all that we need is that AB is a multiple of 2, but we still get a multiple of 4. And so to say this is 2 times nx would be incorrect. It's not necessary to get a full multiple of 4, but it is part of this expression, what we're going to get. That make sense?
Yeah.
Cool. Because now we could just factor out a 2. And you're right, we just get that this is equal to 2 times some natural number, namely 2nx. And then I think from there, let's not raise the definitions. And then from there, once we know that AB is a multiple of 2, that's going to then tell us that AB is even. Probably shouldn't have erased the claim. Oh well. Thus, AB is a multiple of 2. So AB must be. In other words, our original statement P, which said that AB is odd, has to be false. So we've proven that the negation of P has to be true if we assume that the negation of Q and the negation of R are both true. If we want, we could even say at the end, since not P and not Q implies not R is a tautology, or blah, 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 not Q and not R implies not P is a tautology, I should say. Since not Q and not R implies not P is a tautology, P implies Q or R must also be a tautology. So by proving it's the contrapositive of our original claim, we also prove our original claim at the same time. The moral of the story is sometimes if you get stuck proving your original claim, then it sometimes is easier to just look at the contrapositive of your claim instead and try and prove that. Starting with P, it was hard to find a way to get from statement P being true to statement Q or statement R being true. But it was actually not so bad to start from not Q and not R and being able to show not P. And so proving the contrapositive of our original statement allowed us to once again prove the original statement. So sometimes it's hard, I think, to tell when is it going to be useful to prove the contrapositive of a statement as opposed to proving the original statement. I think, in general, if you get stuck early on trying to prove the original statement, sort of like what we did, I erased it, but sort of like we did when we assumed AB is odd and couldn't figure out a way to say anything about A or B individually, then going back and actually proving that not Q and not R implies not P, proving the contrapositive sometimes can be a helpful tool. And as always, if you're struggling to take an implication and find what its contrapositive is, I think it can be helpful to write it out in symbolic form like this, because we've had plenty of practice at this point taking a symbolic form of a statement and finding what is the contrapositive going to look like. Questions, comments, concerns? Okay, so last proof technique in this packet I'm going to talk about is the technique of reductio ad absurdum. So, reductio ad absurdum is kind of the fancy name that a philosopher would use to refer to the technique called proof by contradiction. And the essential essence, totally butchered the pronunciation, the essential essence of reductio ad absurdum, or proof by contradiction, is you have a statement P, and you want to show that statement P is true, and you can't show that statement P is true by any other way. What you can do is you can assume that your statement is false, and then show that you arrive at a logical contradiction. So the way this works is to prove statement P must be true. Assume P is false and show a logical contradiction must occur. Because if you could show that, because if you know that whenever a statement P is false, a logical contradiction occurs, that tells you P can't possibly be false, and therefore P is true. How many of you have ever heard of the Socratic method before? Kind of discourse. A lot of you have? This is the same thing as the Socratic method. So let's say you were to make a claim, and the claim is, I don't know, the world is flat. The way that you could prove that the way that the Socratic method seeks to show that that statement is false, the world is flat, would be, if I were Socrates, to say something like, okay, so you assume the world is flat. Then that means that the world has to have an edge to it, right? Therefore, the world has four corners. Since it's flat, it has to have corners. Therefore, there has to be four different points in the world where there are corners to the world. But there are no points on Earth where there are four corners to the world. The Earth's been mapped out. At no 4 points can you see that there are corners. Therefore, we have arrived at a logical contradiction. Your original claim that the Earth was flat has to be false. You are a fool. Get out of my class. Good day, sir. And that's how the Socratic method works. You want to show something is true, that the world is not flat. You assume the opposite of that, and then you sort of logic your way to saying, well, if we assume that your statement P is false, if the world is not actually flat, then what sorts of logical connections does that lead to? And at some point you can show, aha, we've reached something that something would have to be true that can't possibly be true without causing a contradiction. Therefore, the original statement P had to be true, as the assumption that your statement P was false led to fallacies and contradictions and terrible, terrible things, logically speaking. And so that's kind of the general way that reductio ad absurdum works, is that to prove a statement is true, you just show that it can't be false. That if it is false, then you're in for a bad time. Let's look at an example. So I'm going to make a claim that no number A is both even and odd. Something that should feel maybe intuitively obvious. Yeah, if it's even, it can't be odd. If it's odd, it can't be even. But this is still something that remains to be, that we can actually show. But how would we prove this claim? This claim's kind of difficult to prove. Because it's not an implication. We can't start by saying, assume A is even or anything. And we could, but it'd be difficult. And this isn't an implication, so we can't just take its contrapositive either. So this whole thing is going to be my statement P this time, that no number A is both even and odd. So if we want to show that our statement P always has to be true, by the way, PF, just so you remember, stands for proof. It's my shorthand. if we want to use the method of reductio ad absurdum to actually prove that our statement P, no number A is both even and odd, has to be true, what do we want to start by assuming?
Number A can be both even and odd.
Yeah, we're going to assume the negation of P. So in order to prove P is true, we're going to assume that the negation of P is true, and then show somewhere along the lines we're going to have a logical contradiction. So what would it mean? What would it mean to negate the statement no number A is both even and odd? This one harks back to standard 2, I believe, where we're talking about how do you negate a quantifier. So if it's false that no number is both even and odd, what would have to be true?
At least one number A is both even and odd.
Yeah, the negation of this would be at least one number A is both even and odd. So let's assume that. So let's assume there is, I'm just going to say there is a number A that is both even and odd. Because if it's false that no both even and odd number exists, then it has to be true that we can find at least one. There may be more, but there's at least one out there that will do the job. So if A is both even and odd, what can we say about the number A?
Then A would have to equal both 2n and 2n plus 1 for some natural number n.
Yeah, then we would have to say that A is equal to 2n for some natural number n. And A is equal to, what was the other thing you said A had to be equal to?
2n plus 1.
I don't think A would have to be the same 2n plus 1. Because maybe if A is even, then A has to be equal to some 2n. But if A is also odd, A I think could be equal to some 2x plus 1, or x and n are not necessarily the same. Because that would still satisfy the definition of A being even and odd. If A was equal to 2n, and if A is equal to 2x plus 1 for numbers x and n that may be different from each other.
Okay.
We're still going to arrive at a logical contradiction. It'll just take us a couple extra steps. So we have that A is equal to 2n plus, and A is simultaneously going to be equal to 2x plus 1 for some natural numbers n and x. So if A is equal to 2n, and if A is equal to 2x plus 1, what does that tell us about the relationship between n and x?
And consider that those 2x plus 1.
Yeah. If A is equal to both these two expressions, 2n and 2x plus 1, then it would have to be the case that 2n and 2x plus 1 are also going to be equal to each other. And here's where we're going to arrive at our contradiction. It's not immediate as it's not as immediate as saying 2n equals 2n plus 1, which can't happen. But if 2n is equal to 2x plus 1, I claim we can divide both sides by 2. And on the left-hand side, if we divide by 2, we get n. On the right-hand side, if we divide by 2, we're going to get x plus 1/2. And if n is equal to x plus 1/2, well, I've claimed that tells us that 1/2 is going to be equal to n minus x. And here's the kicker. If n and x are both counting numbers, like 1, 2, 3, 4, 5, 6, etc., if we take n minus x, could we get 1/2? No, we're going to get back another counting number, or potentially a negative counting number. This is going to be our logical contradiction. But n minus x can't, or n minus x has to be a counting number. Or it's negative. So n minus x can't equal 1/2. Aha! If we were at the time of Socrates, this is where I would kick you out of the class. Not really. But aha! We have arrived at a logical contradiction. If A is both even and odd, we have shown something has to happen which can't possibly happen, which is that we've taken the difference of two counting numbers, two natural numbers, and ended up with a fraction, 1/2. This is a logical contradiction. And so no such number can exist. No number can exist that is both even and odd. So what did we do? We started by making a claim, which is that no number is both even and odd. We didn't know how to show this directly. This wasn't an implication or anything, so we didn't know how to prove this using sort of the method of contrapositive we've developed, or the method where we just start by assuming something in hypothesis and show our conclusion has to be true. And so we were able to use this powerful technique, reductio ad absurdum, and in doing so, we were able to say, if not negation of P is true, meaning if P is false, we start with that assumption that ultimately leads us to a point where things go terribly wrong, or we've arrived at a logical contradiction. What questions do you all have about this?
If you had started out, this is probably a dumb, confusing question for people. So,
Oh, those are my favorite kinds of questions.
So if you had started out and made an implication instead of, if you had made the implication, if A, then B and C, then even and odd, right? Then Q, or if P, then Q and R. Could you have accomplished the same thing with that, or is that different because you're limiting A to a single number, and here it's being more general and saying there is some number A, or there is no number A?
Yeah, typically when you try and prove like an implication, like if you were to write down the implication, let's say if A is a number, if A is a natural number, then A is even, and odd? Is this like the sort of thing you want to know? Yeah, so that's a good question, I think. If A is a natural number, then A is both even and odd. I would say something like this is actually making a claim that every single number, counting number, has to be both even and odd. And so that's certainly not something that's going to be true. But proving this is false would be different than proving this is true. These are not negations of each other, mainly because this is the same as saying all natural numbers are both even and odd, which, as we've seen before, is the negation of an all statement is not a no number statement. That would just be, to negate this, you would just need to show at least one number is not both even and odd. Which isn't quite what we proved. We showed that we can't have even a single number that's both even and odd. And if you had wanted to rewrite the original claim as an implication, you could have said something like, if A is even, then A cannot be odd. Or if A is odd, then A cannot be even. And that would be a logically equivalent implication to saying no number is both even and odd. And if you wrote it in implication form, you could try and use one of those other proof techniques that we looked at. But I think at some point you would get stuck and need to ultimately resort still to this reductio ad absurdum proof by contradiction technique. It's a good question, but I'm glad you asked. And just to reiterate, don't ever be afraid to ask a question here, even if you feel like it's stupid, because I guarantee you several other people are thinking the same question. Even if it's something that might feel very simple or silly to you, I think it's always worth talking about. I don't want you to ever feel bad for asking a question about something you feel like you don't understand. With that in mind, any other questions or comments about what we did? Okay, let you go a couple minutes early today. So when we come back on Wednesday, we're going to look at more examples of this reductio ad absurdum technique, and I'm going to tell you the story of how a mathematician got thrown off a boat and drowned for daring to make the claim about square root 2. True story. Have a good rest of your day.